One of the concepts that we're supposed to talk about at the start is the difference between a time instant and a time interval. Who wants to take a run at that right now? What's the difference between a time instant and a time interval? Who should I pick on today? Yeah, what's the difference between a time instant and a time interval?
I don't know what time instant is the exact right now, and that time interval is from here to here.
Okay, so would it be a stretch to say that a time instant involves only one look at the clock, whereas a time interval requires two looks at the clock? Does that seem fair? Reasonable? An instant, a single reading of the time. A single point on a time series graph. An interval of 0 seconds. You look at your clock, your watch, your phone, it's 2 o'clock. Mr. Burnett told me a story yesterday. He told me that he phoned someplace for an appointment. And he said, what about 3:50? They said, no, we can't do that. Well, we could do 10 to 4. It's an instant, right? A single reading of the clock. Easy stuff, right? How am I going to be describing interval then, do you think? Is Tia's definition okay? Instant? That's kind of what you said, right? Single look. So what's an interval? It's the difference between two time instants or readings. The time between 2 points on a graph has a duration of greater than 0 seconds. In my case here, 2 hours has passed. You have to look at the clock twice. Okay? So there's a whole different, and this is true for things not just time. They do want me to cover time specifically, but velocity, instantaneous velocity, how fast are you going right now? As opposed to an average velocity, how fast are you going over a certain period of time? Okay? It's really, really basic stuff. They make it way more confusing than it needs to be. People generally get it. I had a student once. Remember, did I tell you guys, if you say something really smart, you'll get your name in the notes somewhere along the way. So Jordan started up a long time ago. That's probably 15 years ago now. Said to me, Mr. Van, is it kind of like the difference between a picture and a movie? It is, isn't it, right? You take a single picture on your phone, right? That's a instant. But if you take video, then it's an interval. Same idea. Does everyone get it? Did you need to write any of that down? Probably not. How many people wrote it down anyways? Because that's how you've been trained to do. Do you regret it now? Sometimes I do this really boring, stupid, lame-o set of notes just to show to you you don't have to write everything down. You could probably have just jotted it down in one sort of little line each, right? That would have been good. That's okay, you guys. That's what I'm training you to do. Let's move on. Okay, so here's what we're going to do over the next month or so. You'll be able to explain basic definitions such as mechanics, kinematics, dynamics, translational motion, variable motion, uniform motion, and frame of reference. You're going to have to know what those things refer to. Convert from meters per second to kilometers per hour and back. You should have been taught that in grade 10. Differentiate, which means tell the difference between position, displacement, and distance. Differentiate between the terms of instant and interval of time. Look at that. I can check that one off already. You go ahead, check it off. Make you feel good, right? Oh yeah, we've already done one thing. That's good. You will be able to draw a DT graph from a written description. From a DT graph, determine displacement, average velocity, and instantaneous velocity. From a VT graph, determine displacement, average velocity, instantaneous velocity, average acceleration, and instantaneous acceleration. Recognize from ticker tape motion the corresponding graphs. Recognize from a DT or VT graph the various types of motion. And solve problems with the kinematics equations. And there's a list of all the equations that we're going to be using. Does that seem like a lot, Anna? No, because it is. Don't miss class. Stay caught up. There's all the, it says 7 lessons, but some of those are going to be more than one day. And there's a couple labs in there as well. and a couple quizzes and stuff. So we're looking at a solid 3 weeks. Basically, as I said before, this is basically going to take care of grade 10 and get everyone sort of at the same starting line here before we move into some new stuff. So follow along, do that highlighter, little or pencil mark or whatever you want to do as I sort of highlight the important things here. I think it looks like we're going to need clickers here eventually. We'll get those when we get a chance. Okay, so kinematics in one dimension. The motion of objects, baseballs, automobiles, joggers, even the sun and moon is an obvious part of everyday life. Motion was undoubtedly the first aspect of the physical world to be thoroughly studied, and this study can be traced back to the ancient civilizations of Asia Minor. Asia Minor is your Greece, your Egypt, your modern-day Iran, that sort of Middle East area down there. Although the ancients acquired significant insight into motion, it was not until comparatively recently, in the 16th and 17th centuries, that our modern understanding of motion was established. Many contributed to this understanding, but as we shall soon see, two individuals stand out above the rest, and they are, of course, Galileo and Newton. And interestingly enough, Newton was born the same year that Galileo died. If you believe in that sort of thing, it's certainly a possibility. The study of the motion of objects and the related concepts of force and energy forms the field called mechanics. There's one of those words from the outline that you need to know. Mechanics is the study of the motion of objects and the related concepts of force and energy. Now I'm going to be challenging you with some preconceptions that you have, some beliefs that you already have that may actually be wrong. So hopefully you're willing enough to say, yeah, I was wrong and I need to rethink that. Okay? That's an important thing. Mechanics is customarily divided into two parts. Kinematics, which is a description of how objects move, and the other one, which is called dynamics, which deals as why they move. That's the forces. So first we're going to talk about, this is Unit 2, first we're going to do kinematics, how they move, and then we're going to talk about why they're moving, which is forces, or dynamics. We start by discussing objects that move without rotating. Such motion is called translational motion. Okay? Do you guys do translations in math class? What does that mean, Dave? Translation. Yeah, like you've got like a box or something, rather than you translate it over an X. But it looks exactly the same, right? Do you ever translate and rotate at the same time? Sometimes, right? And that's challenging, right? Okay, we are only going to deal with straight line motion, translational motion, just forward and backward. Grade 12, we deal with projectiles or things that are being launched in the air, maybe throwing a football or something. Okay? That's what I said right down here. Okay, so let's talk about speed. And I think this was on the test, was it not? So let's review. Speed and velocity are words we often use interchangeably in everyday language. In physics, we make a distinction between them. For now, we're discussing only speed, which refers to how far an object travels in a given time interval. If a car travels 240 kilometers in 3 hours, we say its average speed is 80. How to get 80? 240 divided by 3. In general, the average speed of an object is defined as the distance traveled divided by the time it takes to travel this distance. And symbolically, in a formula, you would write it like this. And I think you've seen that in grade 10. Have you not? You should have. Jason, don't make me come over there. You've seen it in grade 10. Jason, V equals D over T. What's up? What's going on down here, do you think? You don't have that picture? That's too bad. It's kind of funny. Because you got a velociraptor is equal to your distanceraptor divided by your timeraptor. Thank you, thank you. You can get a t-shirt made up with that on. I'm thinking of ordering one for myself. Actually, I'm thinking it'd be a great one to wear on this day. And I just open my shirt like Superman, I'd be wearing it. No, I'm not wearing it today. But I've thought about ordering one. D stands for distance, T stands for time, and for the speed, the bar over the V is the standard symbol meaning average. Okay, so that's something you haven't probably seen yet. If you write the letter V with a bar over it, not the vector symbol, if you go like that, that means average. In fact, in statistics, anytime you put the bar over it, it means average. You guys done mean, median, and mode before? Yeah, and math, what year was that? Grade 8 maybe? Remember? What does the mean? What does the mean mean? Average. What does the median mean? That's the one, if you line them up in order, it's the middle, right? And the mode is most common. Did you know there's symbols for them as well? The median is like this with a tilde, and I think the mode has a dot or a caret over top. I can't remember. There are symbols for that in statistics. We're going to be dealing strictly with V-bar. Average. Okay, go grab a clicker. I knew there was clicker questions coming. Okay, and the answer is 46. Well done, everyone got it, right? You're just going to take 11.5. Why am I telling you? You know how to do it. 11.5 is equal to d over t. The t is 4, so you're going to go 4 times 11.5, and you probably should be able to do that in your head. 4 times 11, 44. Half of 4 is 2. 2 and 44, 46. 46 what? I guess it would be kilometers. Okay, so you guys can do that. That's good. Okay, let's talk about reference frames. Jason, you're a good volunteer. Come and have a seat, Jason. It's going to be awesome. I just want you to sit right there, face that way. That's all you got to do. It's pretty easy. Okay, so Jason and I are on a train. Make the sound first, Jason.
Choo choo.
Oh, I was thinking that. Can we get another volunteer? Sorry. When riding in a train, you may observe a bird flying by overhead and remark that it looks as if it is moving at a speed of 20 kilometers an hour. Go ahead, Jason.
What?
You're riding in a train, and you see a bird flying by overhead, and you remark as if it looks as if the bird is moving at a speed of 20 kilometers an hour. So you say, "Hey,
Hey,
look at that bird! It's
flying.
flying at 20 kilometers an hour."
Probably.
Who hasn't done that? Everyone's done that, right? Sat in a plane and made that statement? No? Does Jason mean it's traveling 20 kilometers per hour with respect to the train or with respect to the ground? In other words, if I'm in the train with him, do I say, "Yes, you're right, Jason, it sure does look like that bird's traveling at 20 kilometers an hour"? Right? Or does someone else, like Anna, who's on the side of the road, she's waving at the people in the train. I say she's waving at the people in the train, and she says, "What are you guys talking about? That bird's flying way faster than that." Go ahead, Anna. What are you guys talking about? That bird's flying way faster.
I can't take that. It's too much.
What are you guys talking about? That bird is flying way faster.
What are you guys talking about? The greatest fun?
See? Oh, yeah. She thinks it's flying way faster than us. We're on a train. Train seats don't do that.
Mine does.
Oh. Every measurement must be made. Don't run away. Every measurement must be made with respect to a frame of reference. I'm on the train. Jason and I are on the train. We have a different frame of reference than Anna does. She's at rest. She's standing still on the ground. We're moving. Okay? For example, while on a train traveling at 9 meters per second, that's Jason, you might notice a person, this will be me, walking past you toward the front of the train at a speed of, say, 2 meters per second. So come on over here so I can get past you. Yeah, okay. So we're both on a train that's moving at 9 meters per second. But I walk past him at 2 meters per second. Okay, got it? Don't worry about it. Well, you gotta go get your clicker yet. So with respect to the ground, so from Anna's point of reference, how fast am I moving? Okay, I'm gonna go through that again because you just realized, oh, I have to remember this and think. Jason and I are riding on a train. What's your clicker? We're traveling at 9 meters per second. I walk past him at 2 meters per second. He says 2. Anna says what? What does Anna say? No one has answered. Did I start it?
Yeah.
Yeah, I started. Okay, Jason and I are riding on a train, just like the bird, right? He sees me, he says, "Hey, Mr. Bennett, you appear to be walking at 2 meters per second." Anna says, "Mr. Bennett, you're walking at..." Fill in the blank. What does Anna say? You're doing fine at it, by the way. No, just my everlasting gratitude. What does Anna say? How fast?
This is a really comfy chair.
Study hard, go to school. You too can have a company chair.
I'm not going to be comfy.
No? Yeah, you know. Other jobs have company chairs too. I do most of my life stand. How fast does Anna see me walking? I'm waiting on 3. The 3 over the 3 sideways people. How many people realize that the answer's on the paper? Yay! It's right there. 11. Right? Anna says, Mr. Bennett, you're walking at 11.
Oh, you're watching at 11.
Thank you. Right? She sees me going faster. How come? Because I'm already moving it. If I'm just standing here on the train, standing beside Jason on the train, she says I'm moving at 9, but I'm also walking, right? You ever walk on those escalators, or yeah, that's good. Want to go back? Yeah, I knew you were going to do that. You know what, the airport, when they have those moving sidewalks? Those are kind of fun, right? Okay, so you see the people walking beside you, right? And then you walk on, you get to go actually faster, right? Okay. Oh, yeah. I was with someone that I'm related to. He's a little younger, a little older than you guys, you'll figure it out. He was walking so slow that the people off the sidewalk were walking faster than him. They were picking up. I don't know how you do that. Anyways, of course, this is the person's speed with respect to the train as a frame of reference. It's always important to specify the frame of reference when stating speed. In everyday life, we usually mean with respect to the earth. Okay? If you just give a speed, like when the cop pulls you over and says, "How fast are you going, Mallory?" You really should say, "How fast are you going with respect to the earth?" Try answering that. When he pulls you over, you can say, "With respect to the earth or with respect to the moon?" They're going to say, "Step on the car." I know, Mr.
You've done that?
No. But it's always fun to see if kids would believe me if I say that. Okay? Anytime you have a speed, you should give with respect to the earth or with some reference frame. If it's not given, which is like 99.9% of the time, it's always with respect to the earth. Have you ever seen the movie Apollo 13 with Tom Hanks? Bill Paxton? You guys ever seen that? You guys are really young. Okay? There's a scene. Apollo 13 is a movie about the Apollo 13 mission. They were supposed to go to the moon. They had an issue. So instead of landing on the moon, they actually had to go around the moon, use the moon's gravity to bring them back to Earth. So they actually got to go to the moon, but they never got to land. They had to kind of look out the window. And in the movie, there's a scene where they have to fire the rocket for a certain period of time, and they needed a fixed point as a frame of reference. And they look up the moon and they use the moon, I think it is, as a frame of reference. They have to burn for 10 seconds. If they burn longer than 10 seconds, they're going to miss the Earth, and they're going to go hurtling past and never come back to Earth. Don't worry, they came back. Watch it sometime. Okay. The values of other physical quantities also depend on the frame of reference. For example, I don't know if I'm on the next page with you guys or not. There is no point telling you that riding Mountain National Park is 100 kilometers away unless I specify 100 kilometers from where. Distances are always measured in some frame of reference. Furthermore, when specifying the motion of an object, it's important to specify not only the speed, but also the direction of motion. For example, if a friend leaves Winnipeg on a jet plane that travels at a speed of 1,000 kilometers an hour, you would like to know in what direction this person is going. Whether it be Toronto, Vancouver, or, heaven forbid, Ottawa. Often we can specify a direction by using the cardinal points. There's a word I might use. I'm not expecting you to use it. It sounds kind of high-tech. Cardinal points are north, east, south, and west. Remember how I said you always got to measure from those in vectors? That's what I'm talking about, the cardinal points. This isn't always convenient, so in physics we often draw a set of coordinate axes as shown to represent a frame of reference. Have you guys done with these kind of things before in math? Of course you have, right? And you all know that plus x is over there, minus x is over there, minus y, plus y. Okay? Sometimes called a Cartesian frame of reference, or Cartesian graph. You guys ever heard that word? You know why it's called Cartesian? Say again?
Mini Carson.
No. Close though. René Descartes, French mathematician, invented it. That's why. Just more useless information that fills my brain. Object position to the right. Okay, all of this stuff right here, basically you already know, right? To the right is positive, to the left is negative, to the up is positive, to the down is negative. There's also three-dimensional motion, right? 3 dimensions means, well, obviously 3 dimensions. I can't get that to come down, can I? If I do this. Right? 3 dimensions, you'd have like this is called the z-axis, and it would be in and out of the screen. Towards you is positive, away from you is negative. Okay, so that does exist as well. If you're navigating a spaceship to the moon, you have to know about 3 dimensions. Although most measurements are made in reference frames fixed on the Earth, it's important to recognize that reference frames other than the Earth are perfectly legitimate. For example, scientific measurements are sometimes made on moving ships and spacecraft and on the moon. Who would like to watch a YouTube video besides me? Do you guys know about the toilet water in Australia thing? You guys know about that? How it goes different way? Has anyone ever stopped to look at which direction the water goes out while you're in Canada? No. There is quite likely amongst you, about half of you, that the water goes this way, and half of you that the water goes this way.
If you can keep your head when all about you are using theirs.
Okay. Complete another fabrication that the toilet water goes the other direction in Australia. You seen that Simpsons episode where they go to the American embassy, right, and they got this big device in America to make the water go the American way? Doesn't really happen. Coriolis effect has no effect on your toilet water. Okay. Do you guys remember how to change units from grade 10? No? Why not, Mallory? You don't know. Okay, well, here's the rule, right? The rule for converting from kilometers per hour to meters per second. Does anyone remember what it is? Converting from kilometers per hour to meters per second. Is it times by 3.6, divide by 3.6, plus 3.6, or times by 1,000? You're converting kilometers per hour to meters per second. Did I say it already? Okay. Do you have an answer? Jagger? Don't know? Not even going to guess? Come on, guess. Might as well. The correct answer is B, divide by 3.6. Did you remember it or did you just guess? Did you Google it up? Here's the rule. This is something you definitely should write down. Kilometers per hour to meters per second is divide by 3.6. Kilometers per hour to meters per second, you divide by 3.6. Now, why is it 3.6? Yeah, how many seconds in an hour, do you know? How many seconds in a minute, actually? No, seconds in a minute. 60. How many minutes in an hour? 60. 60 times 60? 3,600. How many meters in a kilometer? 1,000. So you go 3,600. 3,600 divided by 1,000, and you get 3.6. Here's how I remember. You're going from big units, like kilometers and hours, and you're going to little teeny tiny units like meters per second, so you're going to make smaller by dividing. Can you remember that? Okay. Can you get this one right? I sure hope so. Come on, everyone needs to get this right. Come on. Come on, David. Oh, it's multiplied by 3.6. Meters per second to kilometers per hour is multiplied by 3.6. You're going to have to do that multiple times this semester. Okay? You need to be able to do that without even thinking. Multiple times. Okay. Oh, is that all you got? Is that it? Wow, that doesn't feel like much. Okay. We got like 20 minutes. Usually I have a little less time to cover this because usually I've had a test after. So, I'll give you this time to work on those questions. I don't really want to go on to the next part of that. I'm not going to. I will give you the rest of the time to do those questions. And I'll see if I can put something else up at the end of your video. Take a few minutes and do those, quick. Were you able to come up with the definition for frame of reference? Should I write something down for you? How about we do that? Let's come up with something together. What is a frame of reference? I think they mentioned it in the video. When we did the whole Jason and I on the train and I on the side of the road thing, what were the two different frame of references that were in that example? The train and the ground, right? So would you say that it's a position or a point? And what do you do from that point? Like Anna was talking about how fast the bird was going, she's talking about how fast I was going.
You base your speed on like that.
You take a measurement from? Would it have to be a speed or could it be something else? Could be something else, right? Okay, so a frame of reference is, and I think I'm going to type it so that it's nice and readable here. Frame of reference. And let's make it a bit bigger so you can read it. Frame of reference is a point, a location. A location from which, what? A location from which, how about measurements are taken or made? A location from which measurements are taken. And does it have to be a specific location or it could really be anywhere, right? It's just we're saying that's where we're taking the measurements from. Right? It's the location from which measurements are taken. That's good. Okay, so if we convert 40, 60, 90, and 110, how are we going to convert to meters per second? We're going to, this is number 4, in all cases we're going to divide by 3.6, right? So what's 40? 11.1, that sounds about right. 60? Okay. 0.3? 25, okay. 110? 30.5. If you're doing 110 down the Trans-Canada, you are traveling 30.5 meters per second. How far is 30.5 meters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the wall. 3 of those. T is right. You said it? Down the whole hall. Would you go down that entire hall with your eyes closed, or would you walk down the entire hall like this? Probably not. But that's what you're doing when you're looking at your phone for 1 second driving down the Trans-Canada Highway. Keep that in mind. If we're converting the other way, number 5 here. Here we're going to multiply by 3.6, right? So 5 times 3.6, like that's what, about like 19 or so? What is it? 18 point what? Oh, just 18? Okay. 10 times 3.6 I can do in my head, that's 36. 15 is going to be? 54. 108. Okay, awesome. Okay. You need to be able to do that kind of stuff. I will stop there. Who gets motion sickness in a car? Anyone? Yeah?
Can you read in the car? If so, consider yourself pretty lucky. For about 1/3 of the population, looking at a book while moving along in a car, or boat, or train, or plane, quickly makes them sick to their stomach. But why do we get motion sickness in the first place? Well, believe it or not, scientists aren't exactly sure. The most common theory has to do with mismatched sensory signals. When you travel in a car, your body's getting two very different messages. Your eyes are seeing the inside of the vehicle, which doesn't seem to be moving. Meanwhile, your ear is actually telling your brain you're accelerating. Wait, your ear?
Frame of reference, right?
See, your ear actually has another important function besides hearing. In its innermost part lies a group of structures known as the vestibular system, which gives us our sense of balance and movement. Inside there are three semicircular tubules that can sense rotation, one for each dimension of space. And there are also two hairline sacs that are filled with fluid. So when you move, the fluid shifts and tickles the hairs, telling your brain whether you're moving horizontally or vertically. With all these combined, your body can sense which direction you're moving in, how much you've accelerated, even at what angle. So when you're in the car, your vestibular system correctly senses your movement, but your eyes don't see it, especially if they're glued to a book. The opposite can happen too. Say you're sitting in a movie theater and the camera makes a broad, sweeping move. This time, it's your eyes that think you're moving, while your ear knows that you're sitting still. But why does this conflicting information have to make us feel so terrible? Scientists aren't sure about that either, but they think that there's an evolutionary explanation. You see, both fast-moving vehicles and video recordings have only existed in the last couple of centuries, barely a blink in evolutionary time. For most of our history, there just wasn't that much that could cause this kind of sensory mix-up, except for poisons. And because poisons are not the best thing for survival, our bodies evolved a very direct, but not very pleasant way to get rid of whatever we might have eaten that was causing the confusion. This theory seems pretty reasonable, but it leaves a lot of things unexplained, like why women are more affected by motion sickness than men, or why passengers get more nauseous than drivers. Another theory suggests that the cause may have more to do with the way some unfamiliar situations make it harder to maintain our natural body posture. Studies have shown that being immersed in water or just changing your stance can greatly reduce the effects of motion sickness. But again, we don't really know what's going on. We do know some of the more common remedies for car queasiness, looking at the horizon, chewing gum, taking over-the-counter pills, but none of these are totally reliable, nor can they handle really intense motion sickness. And sometimes the stakes are far higher than just not being bored during a long car ride. At NASA, where astronauts are hurled into space at 17,000 miles per hour, motion sickness is a serious problem. So in addition to researching the latest space-age technologies, NASA also spends a lot of time trying to figure out how to keep astronauts from vomiting up their carefully prepared space rations. Much like understanding the mysteries of sleep or curing the common cold, motion sickness remains one of those seemingly simple problems that, despite amazing scientific progress, we still know very little about. Perhaps one day the exact cause of motion sickness will be found, and with it, a completely effective way to prevent it. But that day is still on the horizon.
There's also some effects, you might know some of you, when you deal with a concussion, your vestibular system gets messed up. And you have to do exercises while sort of reset. I had to do a whole bunch of those. Basically, you have to make yourself sick and recalibrate your vestibular system. Sucks. It works. Okay, so we will pick up there tomorrow.
Yeah, no, don't stop.
You know, I know. You have to do vestibular exercise?
I went back,
Although the latest research allows that doing stuff. There's the right one there, Butler. No? You think what? Would you? Yeah, tell them I'm going to start tasting.